BA Geography, Geographic Information System, Lesson 10, Data Editing and Errors. In the previous chapters, we have discussed about how and the data can be converted into digitized format to geometric transformation, various methods involved in it, root mean square error method, control points, etc. In this chapter, we will get to discuss about different data editing options and different errors that are occurring during data entry into GIS system. Objectives. Accurate and good quality spatial data are the basic requirement for GIS application. To meet the requirement, we rely on spatial data editing in this chapter. We will discuss about the location errors, spatial data accuracy standards, topological errors, topological editing, non-topological editing and other editing options. Newly digitized layers, no matter how carefully prepared, always have some digitizing errors. They must be checked against the original source to locate the errors. Existing layers may be outdated. They can be revised by using the rectified aerial photographs or satellite images as references. A mobile GIS has become a more common. The data collected in the field can be also downloaded for updating the existing database. A new development in mobile GIS is web editing, which allows users to perform simple editing tasks such as adding, deleting and modifying feature outline. Spatial data editing does not apply to raster data because the raster data model uses a regular grid and fixed cells. Vector data, on the other hand, can have locational errors and topological errors. Location errors such as missing polygons or distorted lines related to geometric inaccuracies of spatial features, whereas topological errors such as dangling lines and unclosed polygons relate to topological inconsistency between spatial features. To correct location errors, we often have to reshape individual lines and digitize new lines. When two layers share some common boundaries, we must make sure that these boundaries are coincident. Spatial data editing can also take the form of simplification and smoothing of map features. The use of both topological and non-topological data in GIS and the presence of the geo-rational and the object-based data models have significantly expanded the scope of spatial data editing. Thus, determining which method to use for a given data set has become the main challenge in spatial data editing. Location errors. There can be geometric inaccuracy in digitizing the land features. These errors can vary by this data source used for digitizing. This type of error is called location errors. Location errors using primary data sources. Although paper maps are still an important source for spatial data entry, new data entry methods using global positioning system and remote sensing imagery can bypass printed maps and map generalization practices. The resolution for the measuring instrument determines the accuracy of spatial data collected by GPS or satellite images where map scale has no meaning. The spatial resolution of satellite image can range from less than 1 meter to 1 kilometer. Similarly, the spatial resolution of GPS point data can range from several millimeters to 10 meters or higher. Location errors using secondary data sources. If GIS database is created from digitizing the secondary data source, for example, a paper map, then the evaluation of the location errors typically begins by comparing the digitized map with the source map. The obvious goal in digitizing is to duplicate the source map in digital format. A check plot can be used to determine the process of achievement. Check plot of the digitized map at the same scale is a source map superimposed to a plot on the source map, and see how much well they match. There are no federal standards on determining how digitized map should be match the source map. This decision is made by the geospatial data provider on the tolerance of location error. For example, an agency can stipulate that each digitized line shall be within 0.1 inch line width of the source map at the scale of 1:24,000. This tolerance represents 20 feet on the ground. Spatial features digitized from a source map can only be as accurate as the source map itself. A variety of factors can affect the accuracy of the source map. Perhaps the most important factor is the map scale. The accuracy of a map feature is less reliable on 1:1 lakh scale map than on 1:24,000 scale map. Map scale also influences the level of detail on published map. Causes for digitizing errors. There are three common scenarios for the errors to be caused between the digitized line and the lines on the source map. The first common reason is the human errors in manual digitizing. This is very common error as it is very difficult to understand when the source map has hundreds of polygons and thousands of lines. One can easily miss some lines and connect the wrong points or digitize the same lines twice or even more times. Because of the high resolution of a digitizing table, duplicate lines will not be on the top of one another but will form to intersect a series of tiny polygons. The second scenario consists of errors in scanning and tracing. This problem in scanning algorithm occurs when raster line meets or intersects or too close together or too wide or too thin and broken. This digitizing error from tracing includes collapsed lines, mishappening lines and extra lines. Duplicate lines can also occur in tracing because semi-automatic tracing follows continuous lines even if some of the lines have already been traced. Third scenario consists of errors in converting the digitized map into real world coordinates, which has been covered in geometric transformation chapter. To make a check plot at the same scale as the source map, we must use a set of control points to convert newly digitized map into real world coordinates. With erroneous control points, this conversion can cause discrepancies between digitized lines and source lines. Unlike seemingly random errors from the first two scenarios, discrepancies from geometric transformation often exhibit regular pattern. To correct these type of location errors, we must redigitize control points and rerun geometric transformation. Spatial data accuracy standards. As users of spatial data, we typically do not conduct the testing of location errors but rely on published standards in evaluating data accuracy. Spatial data accuracy standards have evolved as maps have changed from printed to digital format. In the United States, the development of spatial data accuracy standard has gone three phases. Revised and adopted in 1947, the US National Map Accuracy Standards (NMAS) sets the accuracy standards for publishing maps such as topographic maps from the US Geological Survey. The standards for horizontal accuracy require that no more than 10% of the well-defined map points tested shall be more than 1/30 inch at a scale larger than 1:20,000 and 1/50 inch at scales of 1:20,000 or smaller. This means a threshold value of 40 feet on the ground for 1:24,000 scale maps and about 167 feet on the ground for 1:1 lakh scale maps. In 1990, the American Society for Photogrammetry and Remote Sensing (ASPRS) published accuracy standard for large scale maps. The ASPRS defines the horizontal accuracy in the terms of root mean square error instead of fixed threshold values. The ASPRS standards stipulate the threshold root mean square error of 16.7 feet for 1:20,000 scale map. In 1998, the Federal Geographic Data Committee, a committee representing 17 federal agencies at that time, established the national standard for spatial data accuracy to replace the NSSDA. The NSSDA follows the ASPRS accuracy standards, but extends to the map scale smaller than 1:20,000. Given the new accuracy standards, we must ask for the product specification and determine ourselves if the level of data accuracy is acceptable for the GIS project. Data accuracy should not be confused with data precision. Spatial data accuracy means how close the recorded location of a spatial feature is to its location on the ground, whereas data precision measures how exactly the location is recorded. Distances may be measured with decimal digits or rounded off to the nearest meter or foot. Likewise, a number can be stored in the computer as integers or floating points. Topological errors. When there are errors related to topological relationships that are either required by the GIS package or defined by the user are called as topological errors. 𝗖𝗓 incorporates topological relationships of connectivity, area definition and contiguity. If they are given digitized data did not follow these relationships, then they have topological errors. 𝗖𝗓 also has given 27 topological rules for a geodatabase that governs the spatial relationships of a point, line and polygon features. Some of these rules relate to features within a feature class, where others relate to two or more participating feature classes. Using a geodatabase, we can choose the topological relationship to implement in the data set and define the kinds of topological errors that are important to a project. Topological error with geometric feature. The polygon feature which are associated with topological errors are usually included unclosed polygons, gap between polygons and overlapping polygons. A common topological error with a line feature occurs when they do not meet perfectly at the point that is a node. This type of error becomes an undershoot if a gap exists between the lines and overshoot if the align is overextended. The result in both cases is a dangling node at the end of a dangle. Dangling nodes are, however, acceptable in special cases such as those attached to dead end streets and small tributaries. A pseudo node appears along a continuous line and divides the line unnecessarily into separate lines. Some pseudo nodes are, however, acceptable, for example, including the insertion of pseudo nodes at points where the attribute values of aligned features change. The direction of a line may become a topological error. Point features have few topological errors. The georational data model requires a label point to link a polygon to its attribute. A polygon should therefore have one and only one label point. An error occurs if a polygon has 0 or multiple label points. Unclosed polygons are often the cause of errors with multiple label points. When a gap exists between two polygons, they are treated topologically as a single polygon, which has an error if the label point has already been assigned to each polygon. The geodatabase may also require for some data sets that a polygon contain a point feature, such as a parcel containing an address point. Topological editing. Topological editing ensures that digitized spatial features follow the topological relationship that are either built into a data model or specified by the user. To perform topological editing, we must use a topology based GIS package that can detect and display topological errors and have tools to remove them. Commercial GIS packages have similar capabilities in fixing topological errors with geometric features. Using ArcGIS as an example, group of topological editing tools into three general categories: topological editing on coverages, editing using map topology, editing using topology rules. Topological editing on coverages. Although coverage has been replaced by shapefiles and geodatabase, many editing tools on coverages still remain in ArcGIS. A topological editing on a coverage typically starts by constructing its topology. ArcGIS has a clean command which not only builds topology but also applies a dangle length and physi tolerance to the entire coverage to remove some digitizing errors. For individual features rather than for the entire coverage, ArcGIS has comments that can snap points and lines within specified tolerances. Editing using map topology. The map topology is a temporary set of topological relationship between the parts of the features that are supposed to be coincident. For example, a map topology can be built between the land use layers and a soil layers to ensure that their outlines are coincident. Layers participating in a map topology can be shapefiles or geodatabase features, classes, but not coverages. Student features in a map topology are defined by a cluster of tolerances which can snap vertices and lines if they fall within the specified tolerances. Editing using topology rules. The geodatabase has 27 topology rules for point, line and polygon features. Editing with a topology which involves three basic steps. First step creates a new topology with a defined the participating feature classes. In a feature data set, the ranks for each feature classes the topology rules in a cluster tolerance. The second step is validation of topography. This step evaluates the topology rule and create errors indicating those features that have violated the topology rules. Validation results are saved into topology layer which is used in the third step for fixing errors and accepting. Arrows as an exception, the geodatabase provides a set of tools for fixing topological errors. Topological editing refers to a variety of basic editing options that can modify simple features and can create new features from existing features. Like topological editing, many of these basic operations also use the snapping tolerances to snap points and lines and polygons schedules to edit features. Editing existing features. This summarizes non-topological or basic editing options on existing features. Extend or trim lines. One can extend or trim a line to meet a target line. Delete or move features. One can delete or move one or more selected features which may be points, lines or polygons. Reshaping features. One can alter the shape of a line by moving, deleting or adding vertices on the line. Creating features from existing features. These are the non-topological operations that can create new features from existing features. Merge features. One can group selected line or polygon feature into one feature if the merged feature are not specifically adjacent. They form a multi-part polygon which is allowable for the shapefile and geodatabase. Buffer feature. One can create a buffer around a line or a polygon feature at a specified distance. Union feature. One can combine features from different layers into one feature. This operation differs from merge operation because it works with different layers rather than a single layer. Intersect feature. One can create a new feature from intersection of the overlapped feature in a different layers. Other editing operations. Edge matching, line simplification and line smoothing are examples of editing operation that cannot be classified as either topological or non-topological. Edge matching. Edge matching matches lines along the edge of a layer to the lines of an adjacent layer so that the lines are continuous across the border between the layers. For example, edge matching is required for constructing a regional highway layer that is made of several state highway layers digitized and edited separately. Errors between these layers are often very small, but unless they are removed, the regional highway layer cannot be used for such operation as shortest path analysis. Edge matching can be performed on one pair of vertices or multiple pairs at a time. After edge matching is complete, the source layer and the target layer can be merged into a single layer and the artificial borders operating the two layers can be dissolved. Line simplification refers to the process of simplifying or generalizing a line by removing some of its points. Line simplification is a common practice in map display and a common topic under generalization in digital cartography and GIS. When a map digitized from 1:1 lakh scale source map is displayed at 1:1 crore scale, lines becomes jumbled and fuzzy because of the reduced map space. Line simplification can also be important for GIS analysis that uses every point that makes up a line. Lines with too many points do not necessarily improve the result of analysis but will require more processing time. Line smoothing refers to the process of reshaping lines by using some mathematical functions such as splines. Line monitoring is perhaps most important for data display. Summary. In this chapter, we understood how important is editing option as it allows to increase the accuracy and the quality of the spatial data. The operations like topological editing, non-topological editing feature and other editing operation helps in decreasing the topological errors caused either from primary data or secondary data sources.